Hey, it's showtime. Welcome to Chill Skills Sporlan Tech Talks. The topic for this episode is low pressure oil level control systems. Thank you for joining us. Here's a shameless promotion for the next webinar we're going to do. John, we haven't even talked about this one yet. We're already talking about the March 4th high pressure oil level control system thing we're going to do. We're talking about low pressure today. Almost premeditatedly, there would have to be a high pressure version.
Indeed.
You know, March 4th is coming up pretty quick, and it kind of sounds like we're doing more than one of these deals per month.
Like two per month.
Two per month. I don't think they're paying us any extra to do that either.
They're not with you?
No.
Really?
Oh, yeah, you're getting extra? I see how
I
it is.
didn't say that.
Yeah.
I didn't say that.
I heard we'll be doing this deal at this kind of a schedule through March, and then it's back to one per month. Of course, that's subject to change. Here are a few instructions. Yeah. If the speaker on your computer doesn't work, maybe it's time to get a new one, or you can simply dial in with your phone. There should be a phone number somewhere on the invitation that you originally received for the webinar. But here it is on the slide, just in case you don't have it handy. Of course, if you already had logged in, you won't be seeing the slide. As we move along and you have questions, you can type those questions into the Q&A window. We plan to answer some questions live. If we run out of time, we'll go back and post answers to those questions online. However, if you hang on and you're patient, it's a good bet that we may answer your question during the course of the webinar. And just so you know, we're recording it. And sometimes we run into broadcasting problems and you can't see it live, but you can go back and listen to the recorded version. It'll appear on Facebook Live first for your listening pleasure, and then later on the Sporlan YouTube channel. And just to let you know, we're here to assist you. During the course of this webinar and at any other time, you can reach our headquarters by calling 636-239-1111. You'll get one of those insidious automated systems, but it'll guide you to a number or to a person, and you'll actually get a human, be it in tech support or in customer service or wherever. You can call tech support directly at 636-392-3906. You can also send us an email at svdtechsupport@parker.com. Hello, I'm Jim Jansen. That's me. That's this guy over here. I guess with the video, I don't even know if we need this slide anymore.
Not anymore.
Yeah. And joining me is John Withouse. Oh, I forgot to say, I'm a senior application engineer, and you can see senior means you got this light shade of fluorescent gray hair. John's got the more dark charcoal gray hair going on here, but I
go for the charcoal gray look.
You like that? You like it better?
Yeah.
He's a senior principal engineer for the Sporlan division. He's a published author, consultant, and I've said this many times in the past, he's an all-around extra smart guy. This means John's a big deal around here, and I'm really excited to have him join us again today. I always, say hi, John.
Good afternoon, Jim, and good afternoon, everybody out there.
We also have Phyllis in the room. She's our communications director. She tells us what to do and when to do it, or at least she thinks she's telling us what to do. And every once in a while, we'll pay attention to what she has to say.
Mm-hmm. We do.
Occasionally, we'll listen to her. Moving along. This is a continuation of the old supermarket seminar series. We used to do a marathon 8-hour presentation for people remotely. And we'd cover everything that we've started doing months ago, all in one day. We're breaking it up into chunks so that it makes more sense and you get a better opportunity to learn something. And we're starting now back on that schedule with these oil level management sessions. Refrigerant oil management. What exactly should be circulating around the vapor compression refrigeration system?
Well, mostly refrigerant.
Is that a good answer? I think so.
I think so.
And how about maybe some lubricants?
Well, that's a good idea too, because compressors tend to not like to run, most of them anyway, tend not to like to run without any kind of lubricant.
Well, I get it. So I guess this oil, historically called that, is required to lubricate the compressor. Mm-hmm. But anything else, the zealots might say, is a contaminant. But that's another subject altogether on its own. Along the way, some of this oil gets pumped out into the system piping and components. Again, oil is necessary to lubricate the compressor. Is it a problem if it doesn't stay in the compressor? Certain system components might benefit from the lubrication that this pumped oil would provide. However, oil has a tendency to adversely affect the heat transfer capabilities of the heat exchangers in the system. Things like condensers and evaporators. Oil and heat exchangers decreases the efficiency of that system component.
Certainly does.
That's where an oil management system comes into the picture. The oil management system works to remove oil from the discharge refrigerant vapor and keep it at the rack and get it back to the compressor, and not allow all of the pumped oil to travel throughout the entire system. This helps to minimize oil return issues and maximize evaporator heat transfer characteristics. In a simple form, an oil separator alone could serve as an oil management system. This could work on a conventional system, a system with one compressor, like this guy right here, and one evaporator. The oil separator functions to detach the oil from the refrigerant vapor being discharged from the compressor. Now, if you want to look at an even more simplistic basis, a typical residential air conditioning system, which also has a vapor compression refrigeration cycle, probably doesn't even have a separator. It relies.
That's true.
Yeah, sorry, John, you're going to say something? I'm talking right over you.
It just relies on good system design to make sure that the oil returns back to the compressor.
And on systems like that, that works pretty good.
Mm-hmm, it does.
But when you've got large, complicated, multiplex supermarket systems, when those are involved, some type of oil management system is almost always required to corral the oil and get it back to the compressor.
Anytime you go beyond one compressor to two compressors, additional considerations have to be made. And as you just pointed out, as you get into these larger multiplex systems with multiple compressors, it gets more complicated.
Yeah, Now let's review this slide. Compressor lubrication. We've got reciprocating compressors. A hermetic may or may not have an oil pump. There's semi-hermetic. There's open drive. There's screw compressors that might require a special type of lubricant. Mm-hmm. Scrolls, they have no pressurized oil system. And then there's even compressors that don't need oil.
That's correct.
Right? And they're what type of compressor doesn't need lubrication? John, come on.
There are some centrifugal compressors out there that run completely oilless. They have things like magnetic bearings.
That sounds expensive.
The technology is getting a little bit more cost effective.
Yeah, and that's me, Mr. Technology. Anybody that knows me. I still have a slide rule. Okay. To keep things in balance, the oil leaving with the refrigerant discharge vapor must equal the oil returning with the refrigerant suction vapor, plus the oil sourced from the reservoir. So we've got that oil returning from the reservoir, oil leaving with the discharge vapor, oil returning with the suction vapor. Now, wait a minute. We haven't even talked about oil reservoirs yet, but we will.
We will.
If this oil gets out into the system, what can be done to get it back to the compressor? That's called oil return, and there can be issues with that process. Here are some things that will contribute to poor oil return once it has made it out into the system. Let's just review this slide. We got things like low load conditions, low refrigerant velocities, improper traps and piping errors, a low charge. We got a compressor that might be short cycling. And this might be a good time, John, to simply, why doesn't the oil that gets out in the system just simply come back with the refrigerant?
Well, there are places out in the system where the oil can be trapped, little low spots that can turn into pools of oil. And sometimes you even run into problems with miscibility, which is the ability of the refrigerant and the oil to mix together.
I'm glad you defined that, because I didn't know what that meant.
You need good miscibility for the refrigerant, particularly liquid refrigerant, to be able to carry the oil along.
I thought miscibility was like you're aiming at something and you missed it, or you hit it. Miscibility, your ability to miss. That's kind of like a near miss. That's not what you mean.
Not exactly.
Okay.
That's an interesting definition, though.
Let's take a look at some of these examples of oil return issues. Now, take a look at this. We got reduced load from reduced airflow that results in reduced refrigerant velocity. John, what could possibly be wrong with the way you see this case loaded with product?
Well,
what's the problem here?
Stocking the shelves is good. Stocking the bottom compartment of the case
is that here?
A little bit over. No, that's actually the return grill. Stocking the shelves in the bottom compartment of the case is good. Stocking the return grill with merchandise is decidedly bad.
Oh, okay. So there is a problem with that.
There is a problem with that. Yeah.
Okay. Now this slide, this is not a number 2 pencils, by the way, in case you mistook it for that. If you've paid attention to some of our previous webinars and you listened to our webinar on thermostatic expansion valves, you might remember that we said the TV is a really great secondary filter. Well, this is an example of that. This is the essentially the pin from a thermostatic expansion valve assembly. Plugged and restricted TV equals high superheat equals low refrigerant flow. Low refrigerant velocity equals oil return problems. Now, here's a nice example of a restriction that could impede the flow of refrigerant and pumped oil. Might be a good idea to replace this, or maybe they were planning to use this as an expansion device.
It would probably work as one.
You think?
Yeah. That's pretty effectively kinked there.
Now, here's another example of a nice inverted trap. Oil and refrigerant might get trapped out here. You got to love this. I used to see this all the time. That Zoom Lock product line that we've got might be able to help fix this rooftop boa constrictor that's going on here right now. Now, what's wrong with this? This looks like nice and clean and neat and all zip tied up in the rafters. What could possibly be wrong with this?
Hashtag, you're doing it wrong.
Is that maybe because there would be a little extra pressure drop through all this excess tubing?
It could be just a touch. Yeah.
Okay.
Just a touch.
I don't know what to say. Appropriate suction line piping design is a critical component in maintaining good refrigerant velocity and oil return. Refrigerant velocity is a very important thing. And features like traps, like you see here, and the correct riser piping design is essential. There are even such things as double risers that maintain appropriate velocities and aid with oil return when the unloading capabilities of the system mandate such a things. Some folks may not be aware of that design technique. And John, it might be a good idea for us to plan to do one of these webinar things on refrigerant piping design.
I think that would be an excellent idea.
We'll need you to do it, that's for sure. Just how much oil are we talking about and why is this a big deal? Well, this slide kind of answers that question. So how much oil does a compressor pump? Now I know the compressor is the device that is used to increase the pressure on superheated refrigerant vapor. That's its main job. Mm-hmm. But in order to lubricate all those moving parts in the compressor, there's some amount of lubricant that passes through it. And a new reciprocating compressors can circulate between 1% and 3% oil by weight compared to the refrigerant. That's a considerable amount of stuff.
It is.
If there's a little bit of wear in the compressor, which occurs over time, especially in a supermarket where you're running these little devils just day and night, you can circulate up to 10%. Now, here's an example of exactly how much that works out to be. So how much oil is in circulation in a typical rack system? Well, if 100 horsepower R404A rack operating at minus 20 degrees, 110 circulates something like 9,310 pounds of refrigerant per hour. I just kind of happen to know that. 93 pounds of oil circulates per hour if it's at that 1% mark.
1%. Mm-hmm.
279 pounds of oil circulates at 3%. Now, I didn't even bother to do the 10% calculation. What would that be, John? How much would that be? Can you do that?
That might be 931. Just
wow.
Going to take a wild guess.
Almost half a ton of lubricant.
Mm-hmm.
Now, we've discussed why the system needs oil or lubricant. We have discussed the compressor's need for that lubricant. The oil does this. It lubricates the compressor, the moving parts in the compressor. We've discussed the oil will travel out into the system with the refrigerant. Now let's start talking about how to manage the oil and get it back to the rack so it can lubricate the compressor. There are a number of different methods to manage the oil in a system. We're going to discuss the low pressure oil management version, the mechanical version. There's a lot of other ways to do this, and along the way, we'll probably talk about those different methods. But what's so special about a low pressure oil management system? Well, here's one thing. The low pressure oil system has a separate oil separator, which you see right here, and oil reservoir. Now, discharge gas leaves the compressor, leaves each one of these compressor, and the oil is removed. The oil that is transported with that refrigerant flow is removed in this separator. And depending upon the design of the separator, it may have very little storage space available to retain that oil and must therefore be supplemented with this oil reservoir. Oil travels up to the oil reservoir, and now the oil pressure of the system at this point is high. It's at discharge pressure because it's connected to the discharge. That makes sense? But wait a minute. I thought we said this was the low pressure oil management system. Let's zoom in on part of the schematic and take a closer look. This is a low pressure system, and here's why. This pressure must be reduced to a pressure slightly higher than compressor crankcase pressure. Now let's take a closer look at that's part of the system. So here's the oil reservoir. The pressure in the oil reservoir is effectively reduced by relieving the pressure above the oil through a vent line to the suction header. This goes over to the suction header. Kind of like allowing the refrigerant to boil out of the oil. The pressure in the oil reservoir is maintained slightly above suction header pressure by means of an oil differential check valve installed in the vent line.
Maintains the proper pressure for later returning it back to the compressor crankcases.
Isn't that slick? The high pressure refrigerant is then bled to the suction line through the oil differential check valve. This valve maintains the oil reservoir at a pressure slightly above suction pressure to guarantee flow of oil to the compressor's oil level control devices. So there you go. Now, I don't want to forget to mention this oil filter and why it's here. Why is that oil filter there, John?
A lot of times the oil is actually one of the places where system contaminants settle out. That's where the oil is, where the system contaminants can wind up in. And if we use an oil filter correctly, we can remove a lot of those contaminants out of the system. We don't have to rely on the regular system
contaminant control devices.
Contaminant control devices, the liquid line filters and the suction filters to do all the work. We can get more effective contaminant control by also using an oil filter.
What a deal. Well, so we move on to slide 21 here. We're now back to the complete diagram. If the oil pressure were to remain at discharge pressure, that high pressure would force the oil level control wide open, causing high oil levels. That's these devices here you see attached to the compressor banks. The oil level control functions by adding oil when the level is low. Now, unfortunately, it cannot easily correct an oil level that is too high. Again, note this oil filter and the oil supply line. That's a critical component. We'll talk about that in depth when we do the high pressure discussion. Now, what's the deal with these oil separators? We talked a little bit about them. We just showed it as a box on the diagram. How do they work? Well, all oil separators work to remove oil from the discharge gas. They're not perfect. They take a big chunk of it out, but they don't get all of it. This example shows an impingement type separator. It's just one example. It's sometimes referred also as a conventional oil separator. As discharge gas enters the vessel, the gas expands to fill the available volume of the separator, and the gas velocity decreases, and those atomized oil droplets collect on the impingement screen. on the surface of that screen, and it separates from the discharge gas. As the oil droplets become larger, they eventually fall to the bottom of the separator and into the reservoir that's available here. As that oil accumulates, it opens the ball float in this example, and that allows high pressure oil to flow over to that oil reservoir. This kind of looks like a gravity kind of device to me. We will discuss a variety of other separators next time when we cover the high pressure version of oil management systems. Now on to the next device in this system, the oil reservoir. Now this is a relatively simple device. What does it do?
It just simply holds the oil that we've now separated out of the discharge gas.
I guess we could call it an oil holder, but it's an oil reservoir. That's a slicker name. Yeah. Many models also have sight glasses to allow the service technician to visually approximate the oil level. Connected to the oil reservoir is the oil differential check valve, that OCV. We talked about that. The OCV, oil differential check valve. You know, I hate it when somebody uses like an abbreviation or an acronym and they don't define what it is. You know, they all, you know, those high level marketing types do that all the time. And corporate management does it all the time. We're just dumb engineers. So we've got to tell you what that acronym means before we use it. The OCV works to maintain the pressure in the oil reservoir at a level slightly above suction pressure. OCVs are available with settings of 20, 25, 30, and 35 PSI differential. And this will all make more sense when we discuss the adjustment procedure for the oil level device. As a high pressure burst of oil travels to the oil reservoir, the pressure in the reservoir naturally increases. The pressure above the setting of the OCV is bled off to the suction side of the system. You could see that if we had the diagram back up. The OCVs are serviceable if they get contaminated and restrict flow through the device. Now, that's the single biggest culprit in almost all these systems, and that's contamination. So measures have to be taken to keep these systems clean. Our products, these valves, control mechanisms are going to fail. Now we're really getting to the heart of the matter. The slightly pressurized oil then travels to the oil level control. The oil level control regulates the flow of oil to the compressor crankcase and maintains a minimum oil level. As the oil level drops in the compressor crankcase, the float in the oil level control is lowered and it opens a needle valve. This allows oil to flow from the oil reservoir to the compressor crankcase. Voila.
Just that simple.
It's just that simple. You can see here that we're indicating that the OL60 is available with a 7-bolt universal flange, and we'll tell you a little bit more about that later. It also has replaced the OL1 and OL2. It's externally adjustable. It's suitable for 90 PSI pressure differential, and it's also available with an equalizer. We'll tell you more about that in a minute as well. Now, oil returns to the compressor via the suction line and the oil level control. Now, adjustments can be made to the oil level device, and this chart shows how it's done. The OL ships from the factory with a setting of 3.5 turns from the top setting, and that's indicated by this vertical line right here. That's the factory setting. The oil level is dependent upon this adjustment and the oil differential pressure. The oil level control adjusted to top position with OCV 20 yields less than a half sight glass level. And you can see that right here, just under a half a sight glass. And I think that's a fairly common oil level specified by a lot of compressor manufacturers. Isn't that right, John?
It is.
Now, if you turn the adjustment stem clockwise, you'll lower the oil level. If you turn the adjustment stem counterclockwise, you raise the oil level, and there's a maximum of 9 turns available in this device. If you get rough with it, you can tear it up. So don't. If higher levels are required, the differential pressure could be increased with a subsequent change in the OCV. You could use the 25, the 30, or the 35. You got choices. An optional oil equalization connection can be found on some models. John, I pulled it off. I said equalization without screwing it up.
That's great.
Thank you. I practiced
I'm
all
very-
night.
yeah.
Night. The equalization fitting, that's right here, allows the oil level controls to be interconnected. If there's multiple compressors in a lineup, you can tie them all together. This permits oil transfer between a series of interconnected compressors. This can help prevent excessively high levels due to a sudden increase in oil returning down the suction line. In this fashion, it does assist or help at least somewhat with maintaining a handle on high levels. And this equalizer, as opposed to the one that you'd find on a thermostatic expansion valve, can be capped if you don't need it.
That's right.
But don't do that on a TEV.
No, don't do that on a TV.
Again, keep in mind, the OL is not a high-level control device and cannot prevent high oil levels following a defrost cycle or a load change. Again, we've already mentioned this. The OL60 replaces the previous OL1 and OL2 models. The OL60 controls with a range of 5 to 90 PSI differential pressure. And you remember that 7-bolt flange? Well, here's a little more information on a little better detail. Why did we do that? That's because there were 3-bolt configurations, 1, 2, 3, and 4-bolt configurations, 1, 2, 3, 4, out in the field. And it just made sense to do something like this to make it more serviceable when it came time to do a replacement. It eliminates the need for oil float adapter kits for 4-bolt whole compressor models. You know, it just makes life easier for everybody. All OL60s are adjustable. That's at 5 to 90 PSI. New models are equipped with that universal 7-bolt flange. Now, you know, it sounds like we got the Department of Redundancies in full motion here because we've said some of this already. The letter designations that you see indicate differences in what are called arms. For some reason, we've decided to call these protrusions arms. But the letter designations talk about arm length, arm number, equalized fitting placement, oil inlet location, and so on. It's always a good idea to check with your wholesaler regarding stock items versus special applications before going out to a job. Just maybe do some advanced planning on this. That could be a really good thing. And again, we've tried to make some universal models here to make life easier for you out in the field. But when needed, there are adapters available to facilitate connecting the oil level device to other compressor models. Now, we didn't list those compressor models here. We've just showed a number of them, and there's a wide variety of them available. And that adapter fits in between the OL and the compressor housing. Now, if you get a hold of a copy of Sporlan Bulletin 122, that's our spare parts bulletin, it lists those compressor models. It's available online at sporlan.com. It's free of charge to look at it, view it, or download it. Oil level control troubleshooting. Diagnosing oil level controls. Frequent problems are system problems and not a defective oil level control. Things like low oil level, insufficient oil in the system, a plugged oil filter. If it plugs up, it did its job. Oil being transferred through the equalizer line. High oil level, oil returning through the suction line. Oil slugs returning from traps during periods of high refrigerant velocity. Excessive oil in the system or the reservoir. Oil being transferred through the equalizer line. That shows up again. Again, the OL is a low-level control device only. And don't forget about refrigerant piping design. That's a critical complementary aspect of all this. If the piping's all messed up, it's not going to matter how good an oil level control system you have in place. Refrigerant velocity is a critical component to system performance and proper oil management. John, the time went by really fast.
It did. I mean, indeed.
They told me I got 30 minutes to finish this. Look at that, 30 minutes. We're wrapping this up. If you got any questions, you could let us know. Again, this is being recorded for your future listening and viewing pleasure, possibly a perfect cure for insomnia. Perhaps. And here it is again, our contact numbers. We're here to assist you with your AC and refrigerant flow control needs. You can reach us at 636-239-1111. You can call tech support directly at 636-392-3906. You can send us an email at svdtechsupport@parker.com. And we're always available 24/7 at sporlan.com for product literature, virtual engineer. That's the Sporlan product selection program and much more. You can view an encore performance of this webinar on Facebook or YouTube. It will appear on Facebook first and on the YouTube channel a little later, but it will eventually be out there for you to view again or to see for the first time. And just so that you don't forget, we got another webinar, March 4th. We're going to talk about high pressure oil level control systems. Now that's less than two full weeks away now at this point, John.
It is.
How are we ever going to be able to take 2 full weeks of vacation these days? I
don't know.
I was going to do that, mow my yard. Wait a minute.
You can't go anywhere anyhow, so,
Okay. All right. This concludes our webinar for today. Thanks for being here with us. Hope you enjoyed it. Hope you learned something. Please join us next time.